So today we want to break down 4 quick slides on going in circles here, okay? So the first idea is distinguishing what's called a revolution versus a rotation, okay? And in real life, we see all sorts of examples. So probably the easiest one to picture is the Earth itself, okay? To distinguish these two. And all it is it's an internal versus external axis, okay? A revolution is when you have a circular motion about something external to the body. So the Earth is a great example as it goes around the sun, okay? What does the Earth do every year? It should go around the sun once, right? And it's 365 and a quarter days, right? Something like that. So actually, it's coming up, right? Don't we got a leap year coming up? So those of you that have February birthdays, you get an extra day to celebrate in the coming year there. Next, a rotation is when you have circular motion about something internal to the body itself. So a great example is when the Earth spins about its internal axis, supposedly every 24 hours, okay? I think technically the Earth is actually getting tired. It's because of earthquakes causing it to wobble about its axis. There's actually a little bit more than 24 hours in a day. So those of you that wish you had more time, in about 10,000 years or so, something like that, it'll be 24 hours in a second. Though I would like to have maybe like 28 hours in a day. That would be kind of nice. Take a nap there, right? So anyway, we want to distinguish a revolution versus rotation. In sports, your coaches, when they help you out, you have to think about both of these. So for example, baseball is a great example, right? When you're pitching a ball and all that there, right? You got rotation about your shoulder, and when you're winding up in your hips and all that, and then the ball itself will spin depending on what kind of pitch you're trying to do, okay? So it's just distinguishing between internal and external axes. Keep it moving. Next slide here. A centripetal force, okay? This is the big idea here that people get confused by. If you think about it, if I throw this ball to Nick, you ready, Nick? There we go. Be careful, there's a fish hook on the end, so I don't want to poke you in the face there, okay? If the ball is going in straight lines towards Nick, what does it naturally want to do? It naturally wants to keep going in a straight line, okay? And there we go. Thank you. You're much more awake than first period. Now, to get it to go into a circle, it's not natural, okay? So to help me accomplish that, I have a string here to pull it into a circle. And hopefully I shove this fish hook in good. If it breaks off, you're stuck, okay? So to pull this into a circle, like a slingshot there you go, I need a string to exert a force towards the center. You see that? So centripetal force is the key here. And notice in the word centripetal, the Latin prefix here means center seeking, is another way to help you remember that, okay? And it turns out that if you think about this, as I throw the ball, let's say it's going towards Nick, towards the back of the room, going up the page here, to get it to go into a circle, it has to accelerate, okay? And we could derive this equation, v squared over r, but we're not going to worry about that. It just takes some advanced geometry and mathematical proofs there. Your book does a pretty good job, but it takes about 20 minutes. We're not going to worry about that there, okay? So here's a big idea. To go into a circle, it depends on 3 factors there, okay? Just using common sense there. If force equals mass times acceleration, then the final equation is mv squared over r. So you tell me, okay? What's going to be easier to turn into a circle here? A car going 20 miles an hour or like a truck going 20 miles an hour? Which one's easier to turn? The car is, right? Because the truck's a lot bigger. It's got a lot more inertia, right? A lot more momentum. So to overcome that inertia, to break it into that turn, it's going to be a lot harder because it's got a greater mass, right? Twice the mass would be twice the centripetal force. Next is the velocity squared versus the radius, okay? So the radius is easy to see. The velocity one's not as intuitive. So if you think about it, when we went racing on our field trip there, those of you that were able to come, it was fun and people drove crazy. The hardest part was on the turns there, right? So is it easier to take a turn wide, like 10 meters, or really tight, like a nice tight 5-meter turn? Which one's easier to do? A nice what? A nice wide turn, right? Because it's harder to break that inertia and make a really tight turn there. So if you take a turn twice as wide, it's going to be half the force versus half as wide there, okay? So radius is an inverse relationship. So the last one is velocity squared. And that one's a little bit harder to see, but all it is it's an exponential relationship is how it works out. So maybe one way to show that is I have a little force sensor demonstration I'm going to do real quick. I got a force sensor here. I'm going to hang my little orange monkey pilot here, okay? And it looks like this thing weighs about 0.2 newtons or so, okay? Now I'm going to spin it in a circle, and it's not going to be very scientific. I'm going to do it about like that, okay? about arm's length. Let's say this is about 40 centimeters, something like that, okay? And the trick is to not like kill anybody or hurt anybody. So if the monkey flies off, just duck really quick, okay? And very unscientifically, I'm going to spin it around about once a second, okay? 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000. Yeah! And we'll try to stop there, okay? Now, I'm going to go ahead and zoom in on my data here. Very scientific, very exciting. There we go. And it looks like I'm averaging about 1.5 newtons or so, okay? Assuming I could spin it constantly there, okay? Now, using common sense, if I took a monkey that was twice as heavy, right, then obviously it's going to take more force or less force to pull it into a circle. More force. So theoretically it should take twice that, like 3 newtons there. And I don't happen to have a plastic monkey that weighs twice as much. But you get that, right? So what's not as intuitive is velocity and radius. So here's what I'm going to do now. I'm going to try to spin this in a circle, let's say twice as small, roughly. Okay? So what do you think? If the circle's twice as small, what should happen to the force? It should be like what? Like twice as much, right? So very unscientific. I should probably just measure this, but that's okay. That takes more brain power. There we go. Let's try that, okay? So about half the radius here, at about the same speed. Here we go. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000. Okay, not doing a good job there because I'm losing control of the monkey there and spraying water all over the place because it's still a little bit wet. So anyway, before it was around 1.5, so theoretically if I was keeping it constant, it should be about double 3, okay? So what's not as obvious though is the speed. So here's what I'm going to do now as I get rid of all the water that I just sprayed all over the place. I'm going to try to spin it twice as fast here, okay? So that means instead of 1 rotation every second, I got to do 2 at the same length. Okay, this requires coordination. And if this cord breaks, just stop, okay? Because I don't think you're actually supposed to do this to the force sensor. But I just thought it would be kind of a cool way to show it. Here we go. Kids, don't do this at home. We're going to go twice as fast. Here we go. 1, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000, 6, 1,000, 7, 1,000, 8, 1,000. Okay, oh yeah, just spraying water all over. Sorry. There we go, just a little bit of water, okay? So it's not very scientific, but twice as fast is definitely not twice the force, okay? Theoretically, it should be 4 times the force, around 6 newtons. I'm just trying to get you to qualitatively see that there, okay? So the big idea is to go into a circle, there's only 3 factors that would affect the amount of force necessary. One is the mass of the object. The second is the velocity of the object, but it's velocity squared. And then the third is the inverse of the radius there, to go into a turn there. In real life, we take advantage of all these factors when it comes to racing, okay? So for a race car driver, you can only control the velocity, the speed of the car, and then the radius. So the trick is you want to brake enough so that the centripetal force to make the turn doesn't overcome the friction or grip of the tires. Otherwise you spin out, which we saw big time on the track on Friday there, right? Craziness. And then the last factor is the radius of the turn. So in racing there's this thing called straightening the corners where you try to take the turns as wide as possible so that you can maximize the velocity and minimize the centripetal force there. In real life, we're not trying to be race car drivers, which is okay, because you shouldn't be an idiot when you drive. Keep the idiot driving on the racetrack there. So if you think about it on a highway, it's a great example. On an exit ramp for a highway, speed limit's usually what? Like 50 miles an hour? Like 25, right? But nobody does 25 miles an hour. So because engineers know that people drive crazy off highways and stuff, there's a little trick. What do they do to the highway to make it easier to make the turn there? They tilt it, okay? So a lot of racetracks, you'll see what's called a bank turn, or like in bobsledding and stuff like that. Big time, you bank the turns there. Because think about it, a bobsled, you have no grip. That's the whole point. It's a sled. It slides all over. So in order for a bobsled to make the turn, you have to have a bank turn so that there's a normal force component that provides that centripetal force to push you in a circle. So highway engineers know that you and I are guilty of going off the exit ramp like at 50 miles an hour. Don't do that, okay? So they tilt it, they bank it to help you make that turn there. Okay? Another crazy example is your laundry machine. Okay? You guys ever think about how your laundry machine dries off your clothes? You ever look inside? There's a little tiny what inside the laundry machine? Little holes, right? So as your laundry machine spins, it looks like the clothes fly out and they stick to the walls there, right? And then the water then flies out in a straight line tangent to the circle. So what's cool is your clothes, they get pushed into a circle from that centripetal force. That's called a centrifuge. And right now we're going to do our own little crazy laundry machine demonstration, show you circular motion. This is crazy. Here we go. Boom. Perfect. Okay. So here we got a cup of water on this platform, this tray. You can hold up a little bit higher, okay? And then here I got our pilot, quote unquote, okay? This could be an astronaut. There we go. An astronaut in a jacuzzi on the International Space Station, okay? So one problem in outer space is you don't have a way to generate artificial gravity, right? So it kind of makes it difficult to bathe, take a bath and all that, or go swimming. So one little trick is if you get a space station spinning, then there's a centripetal force to push everyone into a circle. What it feels like to everybody on the space station, there's a centrifugal force that pins you to the ground there, okay? So here's what we're gonna have Selby do here. He's gonna start to spin this. The problem is if he's not coordinated, this thing might go flying. So I don't want your stuff to get wet. Let's just move everything over this, okay? So really quick, let's think about it, and I'm gonna have you do it, okay? Right now, how many forces are acting on the cup? Let's just think of the cup. There are what? 2. There's weight and the normal force from the platform. The platform is providing that centripetal force towards the center of the circle, which is your hand there, okay? What you're going to do is, let's just think about it. You're not going to do it yet. You're going to get the cup moving towards Colin. Okay, not yet. And as the cup flies towards Colin, it naturally wants to do what? Keep flying towards Colin until it gets all wet. But luckily, there's a platform that provides a what? A centripetal force to push this up into a circle. See that? Now it's flying up towards the ceiling. Why doesn't it hit the ceiling and get Nick all wet here? Because the platform provides a centripetal force to push it instead of towards the ceiling, towards the back of the room. Instead of it being in the back of the room, luckily the platform provides a what? You're getting the idea? A centripetal force to push it down. Now it's flying towards the ground, towards your head. Luckily, it doesn't hit the ground, or like you on a roller coaster, because what's going to break its fall? The platform, right? To push it back up, they said, you got it, right? So in other words, you're just going to kind of keep your shoulder nice and loose, get it going, and then you're going to go nuts, okay? You're going to tilt back, you're going to go cowboy style. This is when it gets dangerous. If any of the strings break, duck. Okay, it's just water, it's a plastic cup. I used to use a glass beaker, but one year we had a really bad year, and normally maybe 1 beaker breaks out of 5 glasses. This is a bad year, so I'm like, no more glass beakers, so it's just a plastic cup. You got it? So the biggest thing is don't hit this behind you, and then when you stop, that's the hard part. You kind of want to slow it down, okay? Just kind of go with it there. You ready, Sally? Here we go. 1 for the money, 2 for the show, 3 to get ready, and 4 to go. Go for it. Here we go. And oi! 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 Okay, cowboy style. Tilt back, and woo! And slow it down, don't change yourself in the head. Okay, stop. Okay, slow down, and oh! Let's give Sally a hand. Good job. Woo! There we go, that was awesome. And nobody died. So think about it, that's exactly like closing a laundry machine, okay? As it spins, the clothes stick to the walls of your laundry machine. Common misconception, okay? You've seen this done like junior high version with a bucket of water, but this is like the real version, okay? What keeps the water in the cup when it's upside down? What keeps you stuck to your seat when you're upside down in a roller coaster? A lot of people think centrifugal force doesn't exist, okay? The answer is nothing. Nothing keeps the water in there. It has inertia. It naturally wants to go in a straight line, okay? The walls of a laundry machine, the seat of a roller coaster, the cup pushes the objects into a circle. You see that? So your laundry machine has little tiny holes. Technically, when it spins, the water flies out in a straight line tangent to the circle. The clothes want to go in a straight line, they get pushed into a circle, okay? So it's confusing because from your point of view, you think that you're getting stuck to the walls, okay? Like this old ride called the Cajun Cliffhanger. Awesome ride where you're spinning around and the floor drops and you're stuck to the walls. But really, there is no centrifugal force. It's your body's natural inertia, okay? That you get stuck to the walls there. Awesome ride other than too much liability, which is why I think Six Flags finally had to shut it down there, okay? So, again, the whole point is there's only a centripetal force. Last slide of notes here. Linear speed is what we already know, going in a straight line. It's the angular one we need to define, okay? To spin in a circle, we don't use meters per second. The technical unit is radians per second. There are 2 pi radians in a circle, so that's 360 degrees, okay? So to get your angular speed, we use this Greek letter omega, lowercase, looks like a lowercase w that's kind of curly there. And all it is it's 2 pi, the distance around a circle, divided by the time for 1 revolution, called the period. Now, we normally don't use radians per second, that's really nerdy. What you're used to is maybe RPMs, revolutions per minute. Where do you guys see that in a car? You got your speedometer, right? And then what do you see RPMs? It's usually right next to it, right? There's a thing called your tachometer, where it shows you your revolutions per minute in your engine. So usually you don't want a red line, right? You got to shift gears there and all that. So anyway, if you multiply 2 pi times the radius, to both sides of the equation, well, wait a second, 2 pi r, that's the equation for the what? Around a circle? The circumference, okay, divided by the time, that's your speed. The speed around a circle, is 2 pi r divided by the time. That's your linear speed. So 2 pi r over t is your velocity, and that's equal to your angular speed times the radius, omega r. Okay? So in other words, you could say that omega is 2 pi over t, but our linear speed is just equal to our angular speed multiplied by the radius. What does that mean? It's a lot of gobbledygook talk. All it is how fast you're moving in a circle just depends on how fast you're spinning and how far you are from the center. That's it. Okay? So in real life, when would you ever use this equation? Great example in the old days was music. Your music was stored on this thing called a CD. And I know that seems like weird, that wow, that's so old. But I remember when I was a kid, when that came out, that was a big deal. Okay? You guys are too young. You guys still know what a CD is, right? So some of our incoming freshmen, they might not have used a CD player before, right? So all it is a CD, I should have grabbed one, has music stored on a circular piece of plastic with a laser, right? And have you seen that laser inside the machine before? Okay. You have to program in this equation, V equals omega r, because if your music is stored on an outside track versus an inside track, it's going to move at a faster data rate on the outside there. So you have to account for that there. Okay? How about you go to Great America and you just ate like Dippin' Dots and a big old turkey leg, and you had another piece of pizza, and you don't want to go too fast. Your little brother or sister wants to go on the merry-go-round. If you don't want to go very fast, you want to sit on the outside seat or on an inside seat? An inside seat, because you won't move very fast. It's a small circle. In the same amount of time, you'll cover less distance. Okay? So to go into circle, to distinguish an angular speed from a linear speed, we come up with this definition called omega for an angular velocity. So now we're going to apply this by doing a little mini lab in your packets. Okay? We're going to go outside and play a game called Crack the Whip. So if you guys